So, what exactly is nonlinear programming, and what are we how are we going to talk about it? So, nonlinear programming is just like a linear programming problem, where either the objective function or at least one of the constraints is nonlinear. So by nonlinear, we mean that instead of all variables being linear, that is variables by themselves raised to the power of 1, or constant terms, instead of that being the case, we are going to have non-linear functions. So you'll have x squares and x cubes and so on. So what we'll do is we'll take a simple example. We'll do a production example in this video, and when I do the synchronous session on Thursday, we will go over a finance example. So that's the plan for that. So one of the terms of the objective or the constraint is nonlinear. Now here are some very simple examples. Price of a bond is nonlinear. Price of stock option, marginal cost of production, demand tends to be nonlinear, and that's what we're going to talk about in class today. So let's take this example. Par Inc. is a manufacturer of medium and high price golf ball bags, and Par's distributors agreed to buy the golf bags that Par produces over the next 3 months. So we're not going to do the unconstrained version of the problem. We're only going to do the constrained version of the problem. So in fact, I'm just going to get rid of this when I post this. I don't want to have that. Okay. Now, consider the case in which the relationship between the price and the quantity sold causes the objective to be nonlinear. And this is a very, very common way of looking at things. Now, in many of the problems that we did, if you remember the chairs and tables problem, we said, okay, make 320 chairs and 320 tables and 360 chairs. There, the assumption was every chair and table that you were manufactured, you were able to sell. And the same goes for all the other examples that we considered. Wherever we considered profit, we were assuming that everything that we manufactured, we potentially are able to sell. But this is not always true. That's because items that are more expensive tend to sell less than items that are less expensive. That's the usual way that things go, except for, of course, luxury goods, which have some special, intangible value that give things like, prestige and the cool factor, or what you want to call it. So there are some intangible factors that come into play, but otherwise, usually what happens in most goods, for most items, is that if a price is higher, the number of units you sell tends to be lower. So demand and price have a relationship, and that's what we're talking about here. So in formulating the linear programming problem, or in this case, nonlinear programming problem, we assume that a company would sell standard and deluxe bags. Depending upon the price of the bags, we can sell all the bags that we produce, that it doesn't depend upon the price of the golf bags. So usually what you see is that there is an inverse relationship between price and demand. As the price goes up, the demand goes down, and so if PS is the price for standard bags and PD is the price for a deluxe bag, this is what you notice. So remember, PS is the price for a standard bag, PD is the price for a deluxe bag, and this is what you actually notice. So what you'll have is, if S is the number of standard bags that you're selling, the number of standard bags that you sell depends upon the price. And this is an inverse relationship. This is called an additive demand model. You might have seen this in your economics classes, where you have demand depending upon the price. This is a linear relationship. Sometimes you can have very complicated nonlinear relationships also, but in this case, we'll take a simple linear additive relationship where you say that. So saying that if the price goes up, then the sales also go up. So technically speaking here, if PS is 0, then S is 2250, which is to say that if the price of the item is $0, then you will sell 2250 standard golf bags. But I mean, that's never true. But let's say that if price is $10, then you're going to sell $10. So 15 times 10 is 150. 2250 minus 150 is 2100. So if price is $10, then you expect to sell 2100 units of standard bags. So you can either write the number of bags that you sell as a function of price, or you can invert it and say, okay, what is the price in terms of the number of bags you sell? So you can solve the equation to show that the price of a standard bag is related to the number of bags this way. So if the number of bags goes up, So for every extra bag that you sell, the price is going to go down. That's the relationship there. Now, the profit is always revenue minus cost. Now, if you assume that the cost of making a bag is $70, that it's a fixed cost of $70, then the total cost is 70 times S. That's how much it costs you to make the bag. But the price of the bag is PS. So PS times S, that is how much money you're going to make. S is the number of units you sell. PS is the price at which you sell the bag. So the total profit that you make is PS times S minus 70 times S. But we know that PS can be written in terms of S. So if I substitute for PS, so if I write 150 minus 1 over 15 times S, here I can find the function. So this is the profit function of selling all the standard bags, right? So this profit function looks like this. And so this is the profit function for the, similarly you can write the profit function for the deluxe bag, assuming that the deluxe bags cost $150 to make. This is the profit function for the deluxe bag. So the total profit will be 80 times S minus 1 over 15 times S squared. Now where did we get this? We get this from here. So 115 here. So it's 150 minus 1 over 15 times S squared here. So 150 times S minus 70 times S will be 80S. So you can do the math here. So it's 80S minus 1 over 15 times S squared. That's the profit contribution that comes from standard bags. Then 150D minus 1 over 5D squared. This is the profit from contribution that comes from deluxe bags. And this is what I want you to notice. The square term here and the square term here. This is what makes it non-linear. So again, you are making two bags. Think of this as chairs and tables. You're making chairs, you're making tables. The only difference between this problem and the chairs and tables problem is that here we are assuming that the price of the chair and the number of chairs that you can sell are related to each other. In the previous case, we did not make that assumption. And you will notice the similarity here. So the operations involved in making the golf bag. So there are 4 departments that the bags go through. And this is how much, this is how long it takes in each of the departments. So cutting and dyeing standard bags takes 7/10 of an hour. Sewing a standard bag takes half an hour. Finishing a standard bag takes 1 hour, and inspection and packaging of a standard bag takes 1/10 of an hour. And these are the times for the deluxe bag. Cutting and dyeing is 1 hour. Sewing is 5/6 of an hour. Finishing is 2/3 of an hour. Inspection packaging is 1/4 of an hour. Maybe let me make this full screen, probably be easier. Now these are the number of hours that are available. So we know how to write these constraints. We'll say 7. So if S is the number of standard bags you make, D is the number of deluxe bag you make, this will be 7/10 times S plus 1 times D is less than 630. So the mathematical programming model, the mathematical model looks like this. So these constraints are very similar to the chairs and tables problems that we had. The time that it takes for a single bag times the number of bags. So all the constraints that you have, they are all regular constraints. All these constraints are linear constraints that are exactly like the constraints that you saw before. The only difference is the objective function that you see here. Now I'm just going to pause this video for a second. I'll come back right now. Right. Okay, I'm back. I'm sorry about that quick break. So what does this mean? Now because all the constraints are linear, your feasible region is still going to be very similar. So for example, if I go down here, you'll notice that this is your feasible region. Now you'll be able to draw, so there are 4 constraints here. You can draw the constraints. You can figure out that all of the feasible region is towards the origin, not the side away from the origin. You shade the feasible region. It looks exactly like this. But the way you find the optimal solution is the optimal solution is still going to be on the boundary. But in the previous case, we said that it is one of the end points of the boundary. But now that's not the case. It won't be one of the endpoints. It will be some point on the boundary, not always the endpoint. And how do we figure out which point it is? Well, it depends upon our objective function. So we take different values for the objective function, and the way this objective function looks, this actually is a equation for a circle. So if you draw this, you'll notice that you're, ellipse. So you're drawing multiple ellipses, one after the other like this. And one of these ellipses just touches one of these constraints. Now, none of the other ellipses just touches the constraint. So that is the optimal region. Now, I do not expect you to solve this problem using the graphical method. I just want to show you what the solution looks like. If you did it with the graphical method, it is almost impossible for you to do this with the graphical method. You will obviously be solving this problem using Excel. Now, nonlinear programming problems where the constraints are all linear, but only the objective is nonlinear are actually very easy to solve, because you remember constraints are the ones that tell you what your optimal solutions are. So as long as the constraints are linear, you're still going to have a feasible region that looks like a regular feasible region. It is only the objective that changes, so we can still figure out what the optimal solution is. The optimal solution will still lie on the edge of the feasible region. Okay, so let's put this problem into Excel and solve it. So my idea is I'm going to put this problem into Excel. I'm going to solve this problem, and then we'll be done with this video. I'll post this on Canvas, and then I'll do a finance example in the synchronous session. Okay, so let's open up an Excel file. So you have a regular bag and a deluxe bag, standard bag, and so S and D, right? So those are decision variables. Let's say S and D, as usually, going to have the left hand side, the right hand side. Yeah. These are my decision variables. You'll notice that everything that we do to set it up in Excel will look exactly the same. It's not going to be different at all. Now, the Markowitz model, we are going to do the Markowitz model in in the synchronous session. I'm sorry about that. The synchronous session on Thursday, but that is going to be slightly different. But even there, the setup and everything looks very, very similar. This is a very nice way of setting up linear programming problems. So I'm not going to deviate from that. All right. So these are my decision variables. Hence the objective. Now the objective, this is where we are going to do something different. Now usually what we do is we put the coefficients here, and then we write a equation here based upon the coefficients. But here I'm going to write the left hand side directly, so that I'm going to leave alone for the time being. But let's write the constraints. So there were 4 constraints. So first was cutting and dyeing. So the cutting and dyeing constraint, so that is 7/10 here. 7/10, and the other was 1. That's the less than or equal to constraint, and the right hand side is 6/30. The next constraint is the sewing constraint. The left hand side is, geez, those numbers are tiny. So half and 5/6. Half and 5/6. This is less than or equal to 600. Then you have the finishing constraint. Less than or equal to 708. That's a weird number. It's okay. So that's 1 2/3. If I know, let's make sure that it is 2/3. Yeah, 2/3, and 1/10 and 1/4. Okay, 1/10 and 1/4. Now, if you're writing fractions, you have to start with an equal to, because it is a formula. This is inspection and packaging. Right, and this is less than or equal to 135. Right, now everything that we do here will be the same as what we did before. So sum product function. Now remember, I'm writing, so be very careful. The sum product function, usually I would write the sum product function for the objective, and then copy it down, but here instead I'm writing it for the first constraint. I am not writing a sum product function for the objective function because the objective is linear. That is the one difference between this problem and all the other problems that we did. Otherwise everything else is very similar. So I'm going to choose the coefficients. I'm going to choose the decision variables, make the decision variables absolute references. There you go. So it's the exact same sum product function that we've been writing, and this I'm going to copy all the way down. So my constraints are done. It's just the objective function that is not done. So the objective function is 80 times s. So 80 times s, 1 over 15 times s minus 1 over 15 times s squared plus 150 times d minus 1 over 5 times d squared. So let's write that formula just as it looks. So it's 80 times s, 80 times s minus 1 over 15 times, don't forget the times, s squared, right? 80 times s minus 1 over 15 times s squared. That's the profit contribution for from the standard bags, plus for the deluxe packs it's 150 times d, right, minus 1 over 5 times d squared. So this function 80 times s minus 1 over 15 times s squared plus 150 times d minus 1 over 5 times d squared, that is my objective function, and that is exactly what this looks like. 80 times s, 1 over 15 times s squared, blah blah blah, right? And that's my objective function, and that's it. So my objective is here, my decision variables are here, my constraints are here. I'm going to put this into solver and solve it like I did before, right? So the one major difference, we do not have coefficients for the objective function. We write the formula for the objective function directly, and that's not the formula we copy. Because all the constraints are linear, I'm going to write the sum product function for the first constraint and just copy that down, and these look exactly the same as before. So let's put it into the solver. Solver right there. Right. The objective in this case is to maximize my profit, right? So that's my profit contribution, D4. And I want to maximize my profit. My decision variables are these two cells, S and D. Oops, I'm sorry. B2 to C2, B to C2. Now the constraints. Now the GRG nonlinear I'm going to leave as GRG nonlinear because obviously this is a nonlinear programming problem. So we're going to leave that as nonlinear. So to this I'm going to add constraints. I'm going to click on add. And all of my constraints are less than or equal to constraints. So all my constraints are here, less than or equal to all the corresponding right hand sides. So all the left hand sides going from B5 to D8, D5 to D8 are less than or equal to F5 through F8. There you go. So that's my that's how I set it up. D4, this is where my objective function is, maximizing profits. B2, C2, that's my decision variables, and 4 constraints, all of them less than or equal to, so I set them all up together, and finally I leave it as nonlinear. I'm going to click on solve. Now it is possible, so let's see what happens. Oh. Solver found a solution. So let's compare my solution to the actual solution, right? Let's see. It looks like I did get the right solution. Now I did get the right solution, but it might not always happen. Especially with nonlinear programming problems, there could always be issues with not getting the solution. So while I am looking for you to, I will definitely subtract a few points if you don't get the right solution, but I'm only going to subtract very few points if you don't get the right solution, and everything else is correctly set up. So if you set everything up correctly in Excel, you have all the equations written on correctly, you set everything up correctly, the only thing you don't get correctly right is the final answer, then you will get 99 out of 100 points. That's how much I don't care about the final answer here. But you still have to set everything up correctly. Everything should look correct in the solver and everything. But if you don't get the right answer, you'll get 99 out of 100. If you get the right answer, you'll get 100 out of 100. right? Now, why am I saying that I do not care if you get the right answer or not is because of how nonlinear programming problems look. So let's take a look. The problem with nonlinear programming problem is that you might not always have something called a global optimum. So you want to find the values of X, in this case, the number of standard bags, the number of deluxe bags, that gives you the maximum profit. But the way the optimization algorithms work is that you might not always find the global optimal. You might end up with something called a local optimum. So local optimum looks something like this. So if you have a function that looks like minus x square minus y square, it has a single maximum value. So all of these other values give you lower value for the function than that. So that there's a single maximum value here. And if you have function x square plus y square, there is a single minimum value here. You can always find the single minimum value here at 0, 0. But if you have a really complicated function like this, so look at this function, it is really complicated. So when you have functions that are decently complicated, your 3D graph looks something like this. So here, there is a minimum here, there is a maximum here, there is another maximum here, but the maximum of all values is here. But sometimes what happens is that the algorithm can get stuck at these values which are called local maximum values. These are local maximum values because the values are maximum in that region, but the global maximum value is this number here. There is one global maximum, but there are 3 local maximum. So only one of them is the global one. So you might not always end up finding the global maximum. You might end up finding one of the local maximum values. That's why it's okay. So even though you won't get 100 out of 100, you'll definitely get 99 out of 100 for that particular problem, right? And that's what I want to talk about. And that's nonlinear programming. So it's very much like linear programming. Usually the objective function is a nonlinear part, but maybe sometimes one of the constraints could also be nonlinear. But either way, that's nonlinear programming. I'm going to end this